Okay, so back in Unit 1, we talked about percents, and we did some calculations with percents. Today, we want to focus on some more problem solving with percents, and then some more difficult problems, and then some common applications of percents that we're going to get into. So just a little bit of a review of our percents. If we have a simple question like profits are estimated at 8% of gross sales. If estimated profits are $12,000 for the month, what are gross sales? Or what were the gross sales for the month? So we have, as always, we talked before, but we always start with the percent. So 8% is 8 over 100. And now not only does that 8 represent something, the 100 also represents something. The 100 will usually represent either the initial amount, the starting amount, or the complete amount, the whole thing. It's usually easiest to define what the other number, the 8 in this case, defines. Profits are estimated at 8%. So 8 is the estimated profits. Now, the other part of that then in this problem is gross sales. So the profits are a portion of the gross sales. So that makes sense then that the 100% in this case will be the gross sales. And now to set up the other half of our proportion, we see what else we have. We have the $12,000. And in this case, we see that that represents profits. Since the profits are on top, we put the $12,000 on top. And now we can cross multiply and divide. 100 times 12,000 divided by 8. Gives us, oops, something wrong. Oh, drop a 0. That's 150,000 is what that should be. There's 150,000 in gross sales for that month. Outside of that, we have to be careful. We have to be careful that we know that what we're being asked for. So if we look at, let's say we look at a medical statistic that out of 820 critical care patients, 123 were fatalities. We'll just say we're lost. Find the percent who survive. Okay, so here we are looking for the percent. So it's blank over 100. On top here, the percent we're looking for says find the percent that survives. Whatever that number is when we find it, that's going to be the survivors. The 100% most likely then is total patients. And as we look at the rest of the problem, we find that there is a total patients, 820 total critical care patients. That goes on bottom. What we don't find is the number of patients that survive. We find 123 were lost, but we don't find the ones that survive. So we have to do a little bit of work to find that number. Out of 820 patients, if 123 were lost, that means by subtracting 697 survive. So that's the number that needs to go in here. We will now cross multiply and divide. 100 times 697 divided by 820 is 85. So 85% of the patients survive. We could also have one like this. Let's say that Pat's gross pay for the month is $6,000. If Pat pays 38% in taxes, how much does Pat get to keep? How much does Pat take home? Okay, so we have the 38%. So we're going to start out 38 over 100. Now the 38% represents taxes. Also in this problem is gross pay. So we're going to assume the 100% seems to match up with the gross. On the other side of this, though, well, gross pay would be $6,000. That matches up. This number is going to give us the amount of taxes, but is that what we're looking for? Well, in this problem, we want to know how much Pat takes home. So we can approach this problem in one of two ways. We can either go ahead and finish this calculation here by cross-multiplying and dividing. 38 times 6,000 divided by 100 gives us $2,280. But that's not our answer. That's the amount of tax. If we want to know how much Pat takes home, we have to go another step. Take the 6,000 minus the 2,280 to get $3,720. That's what Pat takes home. Now, the other way we could have approached this problem, rather than finding the dollar amount and adjusting there, is we could have worked with the percents. We could have said, hey, if Pat pays 38% in taxes, that means 100 minus 38%, or 62%, is what she gets to keep. So instead of finding 38% and subtracting it out like we did here, we could just find 62%. And that would give us $3,720 in a single cross multiplication. What we just talked about there is something called the complement. Since the base of everything is 100%, if there's only two possibilities, like in this case, either Pat pays it in taxes or it's part of Pat's take-home. There's no other things that are going to go into that factor for this problem. I know in real life there are other things like insurance and all that other stuff. But in this case, those are the only two possibilities out of the total. So the total gets split into one of those two directions. So that means that whatever 1% is, the other one has to be 100 minus that. So if we tell you that the taxes are 24%, the take-home pay is 100% minus the 24%, or in this case, that would be 76%. That's what complements are, is they add up to the full thing, or 100%. That idea of complements is pretty powerful when we're looking at discounts. For example, several organizations will negotiate discounts with different suppliers. In fact, for employees, a lot of places now negotiate discounts with cell phone providers and stuff like that. So let's say that you have, through your employer, a negotiated 12% discount on your cell phone plan. So you're looking at plans, and you have a plan that would normally cost $110 per month. You want to know what it's going to cost after your discount. Well, we very easily could jump right in, do the 12% is 12 out of 100, equals blank out of 110. And cross multiplying and dividing is going to give us $13.20. But now the 12% represents the discount. So $13.20 is the discount, not the amount paid. If we want to know the amount paid, we have to take the $110, subtract that discount of $13.20, and we'll come up with $96.80. Now, let's analyze that. The $110, that was full price. $13.20, that was the discount. We subtracted that discount. So the $96.80, that is the amount that we paid after the discount. If we look at that in terms of these complements, we can see that the full amount is 100%. The discount of 12%, if we subtract what's left, is 88%. So when there's a 12% discount, the amount that we have to pay is 88% of the full price. So rather than finding the 12% and subtracting it like we did here, we could have just taken 88%, or the complement of 12%. And 88% of $110 comes out to be $96.80. Now again, in this case, it would be just as easy to find the 12% and add it on as it was to use the 88%. But there are some cases where we don't have an option. We have to use the complement. For example, so after a 9% discount, you pay $972. What was the full price? Well, here you could try to find 9% of the 972 and add it back on, but it wouldn't work. You'd get an incorrect answer. What we need to look at here is we had the full price, we subtracted a discount, and we got the amount that we paid. I put the percents on the left side here. Full price was 100% minus a 9% discount means we paid 91%. So what we're looking for, the amount that we paid, the $972, is 91% of the full price. We're looking for the full price here. So that tells us how to set up our proportion for calculating our percents. We're not dealing with the 9%, we're dealing with 91%, so 91 out of 100. And the $972, since that's the amount after the discount, matches up with the 91. And we go ahead and cross multiply and divide. 100 times 972 divided by 91 is $1,068.13. So before the discount, that's what the total price was. Same goes for percent increase problems. You might look at price increases or things like that. We're going to look at a dosage increase. Let's say the doctor's current order is for 800 milliliters to be infused each hour. The doctor has a new visit with the patient and says to increase the dosage by 6%. So again, for this one, to find the new dosage, we have to increase by 6%. To do that, we can either find the 6%, 6 out of 100 equals blank out of 800. And we cross multiply and divide. 6 times 800 divided by 100 is going to give us 48. So we're increasing that by 48 milliliters per hour, which means we have the 800 milliliters per hour. We're going to add 48 to it, which gives us 848 milliliters per hour. Well, the 800 is the original order. 48 was the increase that we're adding to it. And we end up with the new ordered dose. On the percent side, the original was 100%. We added 6% to it, so our new dosage is 106% of where we started. So then to figure out, if we wanted to find the new dosage, rather than doing 6%, we could have found 106% of the 800. And here, cross multiplying and dividing would have given us the $848, again, in just a single calculation. Now again, in a problem like this, it's about the same amount of work to do it either way, but we can run into problems where it doesn't work. For example, let's say that after an 8% increase, a product costs $450. What was the price before the increase? Okay, again, here you would be tempted to find 8% and add it on. That would not work here. What we have to look at is the fact that we have the old price. We added some sort of an increase to it. We have a new price. Looking at the percents, the old price would have been 100%. We added 8% to it. So our new price is 108%. On the other side, we know that the new price is $450. And we're looking for the old price, or the price from before. So again, we see here that what we're looking at isn't 8%, but 108%. And we see that the 450 goes with the 108. So 450 has to go on top here. And we can cross multiply and divide. 100 times 450 divided by 108 is $416.67. Now, some of you may have tried to do this quick using the 8%. If you had done that, you'd do 8% out of 450. Turns out to be $36. If you'd subtracted $36 from 450, you'd get $414, which is not quite right. You can see that's almost $3 off from what we needed. Okay, now, we also talked a little bit in the last unit about something called the rate method of percents. In the rate method, we turned the percent into a decimal and used it that way. There are some applications where that's very common. For example, you get into sales and working on commission. Using the rate method is extremely common. We might, let's say that you get a 6% commission, and you have weekly sales, or sales for this week at least, of $3,200. What are you going to end up with? Well, you could set this up as 6% as 6 over 100 equals blank over 3,200. But more typically, they'll just run this as a rate. 6% as a rate is 0.06, and they'll just take your sales of 3,200 times 0.06. Giving us $192. Another application where the commission or the rate method is extremely common is in interest. In fact, we're going to start out with simple interest. If you go to calculate simple interest, the simple formula for that is the amount of interest, I, is equal to the principal, which is the amount of money you either invested or the amount of money you borrowed, depending on where you're looking at, times the rate, which is your percent as a decimal, times your time. And your time is always expressed in years. So if I, let's say we choose to invest $4,000, and we find an 8% investment for 3 years. So using simple interest, the amount of interest, I, will be the principal of 4,000 times the rate, 8% is 0.08, time in years is 3 years, ends up being $960. Which means that at the end of the 3 years, I'd have the 4,000 plus the 960 for a total of $4,960. Now, we don't usually use simple interest on something 3 years long. Usually, simple interest is only used on short-term loans or investments. For example, let's say we need to borrow. I run a small construction company in the summers. And occasionally, I don't finish a job and I don't get paid and I have to make payroll for my employees. So I might go to the bank and I might say, I need to borrow $2,500 for 3 months. Just to make sure my payroll stays above. And they tell me, okay, that's fine. Excuse me. We're going to charge you 6% interest. 6% simple interest. So then how much I'm going to have to pay back? Well, first we're going to find the amount of interest, which will be $2,500, times the 6% as a rate becomes 0.06. 3 months now. We've said that time was always expressed in years. So to make 3 months into years, we write it as 3 over 12. We use that same trick a lot with feet and inches as well. Just write it over 12 to become inches or feet from inches. So now we multiply this out. 2,500 times 6% times 3 divided by 12 gives us $37.50. So at the end of those 3 months, I have to pay back the $2,500 plus $37.50. Give me a total of $2,537.50. Any questions so far? Okay. So next, we said that anything over a few months, generally they're not going to use simple interest. They would use something called compound interest. What compound interest is instead of waiting for the very end to figure out the interest and add it in, they add it in every now and then during the term of the investment or during the loan. And once you have that interest, it's part of your balance, so you earn interest on top of that interest in the next round. Hence the word compound. So let's go back to that original example. We had $4,000 at 8% for 3 years. And you'll note in that original form we came up with $4,960 total after the 3 years. We're going to make one little change to it this time. This time it's 8% compounded quarterly. So, from that now, 8% compounded quarterly, we're going to take a look at finding the balance. Well, 3 years, quarterly, of course, means 4 times, or every 1 quarter a year. 3 years times 4 times a year means we're going to have to go through 12 quarters to do this. Let's take a peek. Let's say we start out with $4,000 at 8%, so 0.08, times, well, it's a quarter of a year, so it's 1/4 of a year, which will give us, oh, what's that come out to be? $80 in interest, I believe. So that means we start out the second quarter with 4,000 plus 80, or $4,080. So that means our interest for the second quarter is figured out the 4,080 times 0.08 times 1/4, which gives us $81.60, which we add on. Now, if we look at this, we have to do this every quarter. And we said there are 12 quarters. I don't feel like doing this all 12 times. So let's look for a shortcut. First thing I'm going to look for is right here. This is the rate times the time. 0.08 times 1/4 comes up to 0.02 or 2%. And that makes sense a little bit because the 8% is annual. Since it's divided up into quarters, 8 divided by 4 would be 2. That's 2% per quarter. So at the end of each quarter, they find that 2% and add it into the account. And at the end of the year, that accounts for 8%, or actually slightly more because of the compounding. Now, we also talked about the whole idea that, if we're doing an increase like that, it's 100% plus the percent being added. So 100 plus 2% is 102%. So at the end of each quarter, you have 102% of what you started with. So now we take a look at it from that angle. Start out with 4,000 times 102% is going to be 1.02 as a decimal, as a rate. Gives us 4,080. That's exactly where we ended up here after the first quarter. So then the second quarter, we take 4,080 times 1.02. Again, that's for 102%. We get $4,161.60, which is what we had before as well. If we never actually added it in, but that's what we would have got. So we can see here what we're doing is multiplying by 1.02 for each quarter. There are 12 quarters. We have a method of multiplying by the same number over and over again, and that is an exponent, or a power. So since we're going to multiply by that 1.02 each quarter for 12 quarters, let's just put 12 in there. So this would be 4,000 times 1.02 to the power of 12, giving us 5,072.97. And recall that when we did it simple interest, it was $4,960 even. So the compound interest came out about $133 extra for this problem. Now, since you guys are young, there's an example I want to show all of you based on this compound interest. Right now, most of you are looking at graduating from high school in the next year or so. Leaving high school 18 or 19, maybe even 17 for some of you, and starting college. If you plan on college being a 5-year adventure, depending on where you're going to go, well, let's just say 5 years, which will put you at about 23 years old when you're done with college. So you finish college and you get that first good job making decent money. The reason I bring up the money is because, well, what if you stayed living the way you were in college? Now, most college students, they drive their older car to keep it on the road. They might still live with their parents or live with several roommates to keep their bills down. They try to live as cheaply as possible. So if you were to keep living that way, you could probably save up quite a bit of money that first year. Let's put down $5,000. You might be able to save even more than that if you kept living cheaply and had a good job. But I put down $5,000 because the federal government limits you to $5,000 a year invested in certain types of retirement accounts. Now let's look at retirement. Right now, they've announced the minimum age for retiring to draw full Social Security is 67 for people in my age group. So for you, figure it's going to be 68, 69, something growing every year. So at 68 years old, let's say that you are eligible to draw Social Security, which gives us a difference here of 45 years. Well, over a 45-year period, what percent do you think you could earn on your investments? Well, historically, right now people are saying, well, lucky if I earn 2%. But historically, anything that's invested over the long haul like that, every 20-year period historically has averaged at least 11% per year growth. So let's say that we're going to get 10% here. So we're going to take our $5,000 that we have to invest, and we're going to invest it at 10%. Now, to make it easier on us, we're just going to figure it compounds annually or every year. So that's 110% at the end of the year, for 45 years. So 5,000 times 110 to the power of 45. Which will give us 364,452. The point I'm trying to make here is, this is at 23 years old. You put $5,000 away once and let it sit there, and you're looking at over $350,000 in your retirement account. Now you imagine doing that 3 or 4 years in a row, you're looking at being a millionaire in your retirement. Well, let's say you get out of college at 23 and you decide, you know what, I worked hard, I'm going to play for a while. I want a new car. I want a nicer apartment. I want some toys. Maybe you want a snowmobile or a four-wheeler or something like that. And you decide you're going to wait until you're 30 to start saving for retirement. I know at your age, 30 sounds way over the hill. For me, it's not so much. Anyway, let's assume you put that same $5,000 away at the age of 30, and you can still get the 110%, or the 10%, so use 110. Well, 30 to 68 is now only 38 years. So let's work off of that. Power of 38. So 5,000 times 110, power of 38. 187,021, 187,022. Okay. You can see here by waiting that 6 or 7 years, what you get in your retirement is basically cut in half. Now, I'll scare you a little bit more. Let's say you wait till you're my age. I'm 41 right now. Which means, let's say I put the same 5,000 away. I get the 10% interest, so 110% at the end of the year. But at 41, I only have 27 years to go to hit the whole 68. So let's see what I come up with. So 5,000 times 110 to the power of 27. 65, 550 basically. You can see there, I end up with about 1/6 of what you would have if you started at 23. In fact, we've got a couple minutes. Here, I'm going to throw your homework out there. The homework is going to be on page 78, 1 through 35, the odd. But since we have a few minutes, I want to show you a spreadsheet here pretty quick. Actually, I'll create the spreadsheet for you pretty quick. And let's say we're going to start out with your age, contributions, and balance. And let's say we'll start out at 23 years old. And we're going to track this up to 68. Let's say you're going to put away that $5,000 a year, every year, starting at 23 up to 68. Oops. Okay, let's give this some room and we'll fill this down. Anybody want to guess how much money you'd have at 68 if you put away $5,000 a year and you got that 10%? Significant. Just under $4 million you'd end up with. Now let's do this. We're going to look at two other scenarios. In this first one, what we're going to do is we're going to do the typical person. So the typical kid right out of college says, you know what? I want to play with my money for a while. So they're not going to put any money away. Let's say they go from 23 up to 30. And they start after the age of 30 putting money away. Let's look at this person over here. Let's say they start at 23 and they put the money away. And at 30, they decide, you know what? I'm done. I want to quit. Not going to put any money away. Now you can see over here the person who started at 30, who messed around for a few years and started saving at 30, they're still doing okay. They still got $1.8 million in a retirement account. That's not bad. What do you think is going to happen over here on the person who just saved for a few years and then stopped putting any money away? They still end up better off. 1.8 million, they're still at 2.1 million. This person here saved for 8 years and then spent the next 38 years playing with every penny they made. This person here played with their money for 8 years and then spent the next 38 years saving up. And because of that whole idea of compound interest, they never caught up to that person who only saved for 8 years. What's that? Oh, start early for college? Or for saving for college? Or what do you mean, getting out of college earlier? Or? I'm having a hard time hearing you. I actually used to deal with this a little bit with parents that were saving for their kids' college. You'd talk to them, their children would be like 16 or so, and they'd have $10,000 saved up for college. And that was something I talked to them about, is rather than using that money towards college, unless it was already in a dedicated college savings plan, you can put that money away for your children. If you have an income, if you're at least 16, you can actually start putting away retirement savings. You just can't put away more than what you earn in a year. So you can take that money, instead of putting it towards college, you can put it in a retirement plan. And if you have someone who starts at 16, which is the minimum age, you have to be at least 16. And like I said, you can't put away, if you only make $4,000 for the year, you can only put away $4,000. So let's take this person here, and let's say that they're going to put away $4,200 or whatever is what they earned that year. So they'll take that money out of their college fund and put it away in retirement. And let's say they get another $4,400 the next year, and maybe $2,100 is all that's left in their college fund. So they put that away their third year when they're 18. That little bit put away at 16, 17, and 18 in a retirement plan could end up being over $1 million at age 66 is all I went up to here. So you can see 16, 17, 18, all I put away, that's just a little over $10,000 that I put away between those 3 years. And that is a huge start on your retirement. It's actually very possible, if you start young, to have your retirement completely planned out and done for by the time you're 21. So it's something to think about. Okay, we got about 4 minutes left, so I'm going to let you guys out of here. Remember, your homework is page 78, 1 through 35. No class on Wednesday because of our in-service. Hopefully I answered your question. If I didn't, go ahead and try to ask again. Like I said, I'm having a hard time. The mic is kind of fuzzy. Okay, otherwise we'll see you all on Friday.